Our next speaker is from ISC. It's Ondrej Surý, and we're looking at PQC for DNSSEC. Over to you, Ondrej.
Hi, this is Ondrej. So I'm here to throw some wrenches into the cogs, DNSSEC, potentially. So this is a research I did for my master's thesis, and I'm doing the final exams in 2 days, so wish me luck. There has been some previous studies, and there are some post-quantum algorithms already standardized by NIST. There's also a round 2 of additional digital signing schemes, which introduce a bunch of new algorithms that might have different properties than those that have been already standardized by NIST. And there's also some interesting research, not mine, on the new post-quantum algorithms. So for DNSSEC, I picked a few of them that seems like small enough, fast enough, or combination of 2. There's Hawk, there's obvious pun on Falcon, which has been already standardized. It's lattice-based. There's SQI sign, isogeny-based, and Mayo multivariate-based. I'm not a cryptographer. I'm crypto plumber. So I just plumb the algorithms into DNS and DNSSEC. Antrag is also lattice-based. It's basically like a way how to make Falcons more. So these are the basic sizes. I marked the ones that are small enough to actually fit into the DNSSEC quite well. So SQI sign is the smallest of them all, but it also doesn't have all the properties we need. Hawk, well, the Hawk 256, it has been introduced by the paper, but it's on the challenge level. So it's not even on the NIST level 1, it's smaller than that, but the authors asked the crypto analysts to break the algorithm on this level as well. Implementation status, it's new. So Falcon, it has a nice implementation from the PQ Clean project, embedded, but it needed some tweaking to be used. Hawk, really, the authors produce a really neat code meant for embedding into other projects. So thanks to them, because, well, after seeing all the code here, I think that the cryptographers should not write code. And software engineers should not do cryptography. So SQI sign, Mayo, same story. The authors are focused on getting this to the NIST round 2 challenge. So it's not suitable for external use. It's like CMake project that makes you cry. It doesn't build shared libraries, and if you try to build the shared libraries, there's some assembly that's not position independent, stuff like this. It's very technical, but it hasn't been easy to integrate this into Bind. The Antrag is, again, just code meant for a paper, not for real use. So I had this neat little machine that lives me in my attic. I tested it in winter, so it was still cold. I used some tools, and I tried to eliminate the effect of the hyperthreading and turbo boost and file system. So they should be relatively the measurement should be relatively repeatable. I also not use the assembly versions because it was impossible to do for some of these. So these are just reference implementations. In Bind, there are some branches, and I had to sometimes do some ugly things. So you don't really want to do at the code. Key generation, this is the least important statistics. What surprised me personally is that the sigma for RSA, the algorithm we use right now, is so huge, and apparently this is like expected from what I've been told. This is more interesting. So I took a root zone. I put a new one KSK, one ZSK with the new algorithm and signed them. And this is the time. So the RSA, ECDSA, and ED 25519 are the algorithms that we have in the DNSSEC right now. So these are kind of, the RSA is kind of a baseline. And as you can see, some of the algorithms are really slow. So signing is usually not that huge problem, but if you go from 800 milliseconds to 54,000 milliseconds, that might be a problem for larger zones or some operators that do online signing. But SQI sign, the size is really nice. So it's like pick speed or size right now. For the DNS message sizes, so the red ones are that don't fit into the enlarged buffers. The yellow ones are those sizes that don't fit into the current eDNS buffer size, which is 1232. For the measurements, I'm going to show you next, I increased the size to what has been recommended in some of the IETF RFC. It's 1422. And we can fit some of these algorithms into that size. For the validation, again, the bluish color is which is the fastest one, and SQI sign is again the slowest one. But does it matter? I'll show you. I also did some resolver testing. So this is real world resolver data. And I had a custom root server serving the signed root zone with these algorithms and using DNS shotgun, which is part of the regular Binary testing, thanks to Petra here. And these are the results. So this is just for the comparison. So the ECDSA compared to RSA, basically like no changes. If you haven't seen these graphs, the top ones are the latencies, and it's reverse logarithm graph. So basically what you want is the line to be as to the left and down as much as possible. So this basically means that under 2 seconds you can validate something like 98. You get results for 98 something 99% with the cold cache, and more than 99.5 for the hot cache. Memory state, the left bottom is the CPU, the right bottom is the memory use, which goes up because there's more stuff in the cache. ED, that's Edward curve. Again, algorithm that's not post-quantum, basically no difference. So for the Falcon, that's the orange one. You can see there's quite a big difference. Remember, this is logarithmic, so it goes for the cold cache, it goes from something like 15% unanswered under 1 millisecond to 25. So there's 10% difference between the two algorithms for to get answered under 1 millisecond. The CPU also goes up, and there are some weird artifacts in the memory. I don't know what they are. And I hadn't had time to study that. For Hawk, looks nice, right? There's almost no difference. We can live with that with DNSSEC. The other algorithm that's slightly larger, it has larger keys, but it still can fit into the signed DNS message still can fit into the eDNS buffer size. It also looks good. SQI sign, that's the one that was slower, but very small. And there's kind of difference, as you can see, but it still might work if perhaps the algorithm could be made faster because, you know, the real software engineers will write the implementation, not the cryptographers. We'll see. I'm not, you know, excluding this one yet. Mail has large keys, but small signatures, and it looks like the size of the keys actually don't matter in the normal operation. Again, it could be used. Antrack, same story. So we'll have to wait, basically. We'll have to wait what the NIST comes with in the end, because some of the algorithms could be broken during the NIST process, the NIST challenge. And the good thing is, I'll skip this slide. The good thing is that we still have time, because it's not like we have to switch to post-quantum algorithm that, you know, tomorrow. It could be in 10 years and nobody will care, because it's not important that the stuff that's signed right now by the non-post-quantum algorithms are being validated right now and not in 10 years in the future. So if we switch 10 years in the future to the other different algorithm, that will be still okay. So the future work that still remains, test at different levels of the DNS hierarchy, maybe use some other algorithms. We should probably talk, the DNS community should talk to the cryptographers. It still hasn't been done really. Look at some pseudo-random subdomain patterns, how it looks. Look what will like force rekeying on if you change the DNS keys very often, how it will affect the performance. Implement some other stuff from DNS. Maybe use the optimized implementations for the algorithms, and do some more measurements. And that's it. So the future is not bleak, really. So we have a like way forward with the PQC for DNSSEC, and we don't have to really hurry at the moment. So any questions, or did I melt your brain? Okay, there's a question.
So I'm Christian Hesselman, I'm with SIDN. We have a paper out that will be published actually this week at the Traffic Measurement and Analysis Conference in Denmark, which analyzes 2 of these PQC algorithms in terms of signing speeds. You may be aware of them. I think you collaborated with...
I've seen it and I commented it.
Yeah, okay. But the thing I would like to comment on is that I'm not sure if we have, you know, tens of years to work on this problem, because we know from past research that it might take, you know, up to 7 or 8 years to get deployment of new crypto algorithms in DNSSEC, let's say at a substantial level. So it might be a bit more urgent than you say.
Maybe, but maybe not.
Any more questions from the room, Kathy?
Nothing further in the room, Mark.
Okay, that was way too short. You had 20 minutes, sir. But thank you very much.